Hello everyone. I welcome you all to this series of videos on artificial intelligence. But before we dive into artificial intelligence, really important to understand some aspects of our machines which has enabled the kind of modern AI systems and applications that we see today in this age. One such concept is levels of abstraction, to ignore or hide away some details or information to focus more on some aspect of the system. Okay, so as we move forward, it requires us to change the amount of abstraction needed. Okay, so we need to reveal more and more as we move along. So essentially, we are moving from problem level to machine level. So how to fill in that gap? This is levels of abstraction, also known as levels of transformation. Okay, so what is levels of abstraction? At the top of it, we have a problem. This is a problem in the society. This is a gap that needs to be filled. Okay, this gap ultimately is implemented using electrons. Okay, so these problems would ultimately run on our machines that we have. So we have this gap, right? If we give this problem to a computer scientist or engineer and we tell them to solve it using electrons, how would that be? Would that be easy? Well, it is going to be a nightmare, if not impossible. Okay, so that is why levels of abstraction were introduced to target the problem systematically. Similar activities were grouped to organize teams and people at different levels of abstraction. So this problem would require algorithms to materialize. Algorithms essentially are not equal to programs. So ultimately, these problems would require mathematical modeling, i.e. theorems or formulas that someone has to prove before a programmer could implement it using a programming language. So we have a large spectrum of programming languages. For example, C language is written by Dennis Ritchie in early 70s. Okay, so why are we talking about C language in this age of modern AI? Because of its uniqueness. C language is the mother of all languages. The strength of C lies in its ability to provide low-level access to memory and hardware. These really make C an efficient language, okay, and suitable especially for system programming and embedded systems. C is also popular for portability, so can be compiled and run on various platforms. Okay, then we have the simplicity with strong community support. And then we have, let's say, simple procedural language. However, it's not object oriented, which is why C++ was introduced. In the high level languages, and I'm shortly going to come on high level versus low level language, we have C sharp, and we have Java, and we have Python, king of AI. We have MATLAB, we have dozens of frameworks and languages that gives us a whole arsenal of options. However, C is the mother of all languages. C is more efficient than its high-level counterparts because C has low-level access, okay, to memory and hardware, which is why C is so popular. Its popularity can be judged from the fact that Python offers a version known as Cython. Cython is used for mixing Python with C for efficiency. And then you always have the option of mixing C, C++ with assembly language. And we'll see shortly how assembly is super duper fast. It's very efficient language. Okay, so having said that, I want to make clear distinction between high level and low level language. Okay, so high level language, what first thing that comes to mind is human friendliness. At one spectrum, we have human friendliness, that is flexibility, flexibility of coding. And on the other extreme, we have verbose and complex syntax. It is verbose, okay? So it's a detailed language. So as you move away from hardware, you get the flexibility. And as you move towards the hardware, you gain efficiency. Yes, efficiency. Okay, so it is flexibility versus efficiency. Let me, draw the hierarchies. We have the assembly at one end, then we have C, C++, and Java, and Python, and MATLAB, and dot, 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 many other. So let this be a line, an axis, or a line that points towards hardware. Okay, so as you move along the hardware, let me draw this in this manner to, I hope I draw it correctly and nicely. Okay, so as you move towards hardware, you are losing flexibility. Okay, and as you are moving towards hardware, you are gaining efficiency. So I think this is a good enough distinction between a high level and low level language. Okay. Okay. One thing that I want to make emphasis on assembly language. So you might want to think, why do we need even assembly language in this age of modern AI? So now we know that assembly is a language that is closer to the hardware. And among high level language, C is the most efficient among all high level languages. Okay, so assembly, let's come back to assembly. I want to start by an example, the operating system that we haven't yet talked about. We'll talk about operating system in detail in a second. Okay, operating system, the heart of the operating system is known as the kernel. All right, the kernel is something that is implemented in assembly. How about that? Why? Because a kernel is a code or a module that is carefully debugged. Okay, and secondly, it runs all the time, so it must be efficient, right? So this is an example of how assembly languages till date have a significant use. So if you are able to identify the crucial part of your program by profiling, okay? So you take your application and you profile your application, and you identify using the 80-20 rule, the 20% portion of your program that runs 80% of the time. Because if you take on and you improve the efficiency of the 80% of your code that only runs 20% of the time, you are not going to make any impact. So you need to identify that part of the code, 20 or 10% of the code that runs 80% of the time, and you take that and improve that, possibly implement in assembly. Your program, if it was walking, it's going to fly. Okay, I hope that was it for programming level. All right, so now we want to move on to shift gears, to move from software as a model of computation to hardware as a model of computation. And we have instruction set architecture. Okay, after being able to implement the algorithm into a programming language and knowing the trade-off between the flexibility of a high-level language and efficiency of a low-level language, we also need to know what machine does our programs run on. So ISA are at the heart of it. ISA is the instruction set architecture. ISA is an abstract model of the machine. Okay, so abstract model, as it is neither software or hardware. Okay, so it is basically a manual. Okay, a book of rules, a contract between the software and hardware. As long as these rules are not violated, our programs will run on the machine unhindered. Okay, and then we have the microarchitecture. So microarchitecture is actually implementation of the ISA, of the rules and syntaxes that forms the hardware. This hardware is actually responsible for executing the statements and instructions of our programs. Okay, so this portion actually this portion makes the courses known as computer organization and assembly language and computer architecture, taught in computer science and engineering disciplines. Okay, I have a few lectures in the playlist of Cole. There you can find a crash course on assembly. It's full of animation and graphics to make assembly easier, and it's guaranteed that 1 hour of these 6 lectures would give you a detailed account of assembly and a very closely related concepts to C language. Okay, so it's a relationship between C and assembly language. How the high-level languages are actually compiled to machine code. So the one stop between a high level and machine code is assembly. So all the high-level languages actually get down to assembly, from where it is assembled into an executable or a machine code. Okay, so it's recommended that you go and once in life must watch videos. Then these architectures are actually implemented in logic into digital computations, which are composed of gates. These gates are then implemented in circuits consisting of transistors, capacitors, resistors, etc., etc. And ultimately, these transistors and these components are actually fabricated using electronic fabrication technologies to etch, transistors, which are switches at the nanoscale. Okay, so these switches, we have billions of these switches in our machines, in our modern day machines, and these switches are switched on and off to activate and deactivate various circuits for different purposes and tasks. Okay, so these electrons are actually controlled through our program, level by level translation or transformations. Having said that, coming back to our puzzle, but before that, let me put the question again, but now in a different scenario, where we have all the levels of abstraction except this seemingly small gap. And now I want to put the same question: would it be easier now to implement the problem? Well, still we have a long way to go, as this is a crucial layer. Okay, because without this layer, users would have to interact with the hardware on their own. Okay, so our programs actually interact with the hardware. They have to access many devices. That means they would have to implement all these interfaces uh, on their own. Okay, they have to implement all these interfaces to the many devices inside their programs, making them bulky and inefficient. Okay, so this is the layer that we are talking about, the much awaited puzzle. What is runtime system? Runtime system is composed of two components, the operating system and the compiler. So the compiler are responsible for managing some special regions of the memory. And most of the memory is managed by the operating system. Combined, the operating system and the compiler uh, is called runtime system. Okay, so the operating system actually is another layer of hardware abstraction. So it hides away the hardware from the user. Okay, at the top of it, we have the GUI, graphical user interface, and this is in fact the component that attracts much of the competition between operating systems. Another function that operating system provides is security. Okay, system protection, security for system protection. Okay, one of an extremely important responsibility of the operating system is inter-process communication, which is nothing but simultaneous execution of programs, programs or processes. Then we have the device management. Device management is a crucial component. The operating system provides a standardized access to devices. In order to appreciate standardized access, let me talk a bit more about this concept. Okay, there are a lot of devices that our programs have to interact with. For example, at the lowest level, our programs have to interact with the keyboard and mouse. Okay, this is at the lowest end, slower devices, right? Then our programs have to interact with hard disk drives, or if you're lucky enough, your machines would have solid state devices, expensive but fast. Then our programs might want to interact with the flash drive, okay, and the main memory, also called RAM. Our programs might want to interact with the graphics card, high speed, high speed devices. Okay, so given these different devices, these devices have different requirements. Okay, it has different communication protocols, right? Um, it has various speeds and other specifications. Okay, so in the context of a wide spectrum of characteristics of these devices, the operating system provides uh, a standardized interface to all these devices without the user having to worry about these characteristics. So now you could appreciate the standardized interface, right? So we can also imagine life without the operating system. Okay, that's why we said that without this layer, the layer of operating system, our programs would have had to interact with all these devices and take care of these characteristics, right? So our programs would be bulky and inefficient. Okay, so coming back to the responsibilities and functionalities of the operating system, one responsibility is the resource management. The operating system allocates CPU, memory, I/O devices, and other resources among executing programs. Okay. Then we have virtual memory. Virtual memory is an illusion of contiguous memory by extending RAM with the hard disk. So it is basically a memory management technique that virtualizes RAM by extending some part of hard disk. These were some of the major modules or functionality of the operating system. I have a playlist on operating system on this channel, which is very short video lectures on operating system, short and concise with a lot of animation and graphics for better understanding. Don't miss out these lectures and also the lectures on assembly. Okay, so let's just put a wrapper, additional abstraction wrappers around the software and hardware parts to explain some other aspects. So this is what we have. We have the user software, we have the hardware, and this very important operating system layer of abstraction. Uh, at the top of it, we have system calls. So we use system calls to interact with the hardware. For example, we use a open method system call, giving it some parameters, file name, and we tell it we want to read or write. Okay, so this is that standard interface that I talked about. So with this open, you can access any kind of devices without worrying the broad spectrum of characteristics of these devices. Okay, okay, we have talking about C, we have calloc and malloc, which are functions that request memory from RAM. Okay, so calloc, when memory returns the blocks, the bytes, these bytes are returned without, or we can say, initialized randomly uh, with garbage. And the difference with malloc is that these blocks are returned with initialization to 0. Okay, so these are the system calls through which we actually talk to the hardware. Okay, but before going directly to the hardware, we have a component known as drivers. Okay, so these drivers are also called sub IO kernel. So this is a kernel within the kernel, and the drivers take these system calls, and we have a controller. The controller actually is responsible for talking to the hardware. Okay, so the request is taken, and the controller interacts with the hardware, either gives information from the user or takes information from the hardware. The controller, through the driver, delivers what the user wants, and this is the way how system calls and drivers abstractions are used to interact with the hardware. I hope the levels of abstraction was interesting and made a lot of sense in the context of artificial intelligence. Okay, so these are some advantages of the abstraction. I don't want to go into details. Make sure you are comfortable with it. It it eases problem solving by hiding complexity and simplification and modularity, reuse and composability and scalability and portability and dot dot dot. So these are the advantages of abstraction layer. Next time we talk about technology trends. I hope to see you soon.